Rheology, in its broadest sense, is a study of the relationship between force and deformation in continuous media. In this film, we shall focus our attention on fluids. We have marked a portion of a flow field outside the viscous boundary layer. Here, water behaves almost like an inviscid fluid. In the model of the inviscid fluid, the basic assumption behind the stress-deformation relation, whether the fluid is at equilibrium or in motion, is that there are no shear stresses, or, equivalently, that the pressure is isotropic. This statement, when combined with the balance of momentum equation, leads to Euler's equation of motion. In this flow, glycerin shows evidence of shear stresses. Water and glycerin are two of many fluids that behave in a manner called Newtonian. With no relative motion, the Newtonian fluid has no shear stresses. The pressure is isotropic. In relative motion, however, the stresses are linear functions of the instantaneous velocity gradients. If we formulate this stress-deformation relation for the Newtonian fluid so that it is independent of the observer and couple it with momentum equations, we obtain the Navier-Stokes equation. There are many situations, however, for which these models are quite inadequate. This is especially the case when you are dealing with materials containing large molecules. This ball, for example, bounces quite vigorously, like an elastic solid. Yet, it really is a fluid. We'll come back to it later. Here's a viscous material, which I can pour into this beaker. No, I think I'll use this beaker instead. I can even cut it to length. This material is a solution of a high polymer. Some other materials that do not follow the simple Newtonian model are molten plastics, egg white, paint, and mayonnaise. Mayonnaise holds its shape if you let it alone, yet it spreads with ease. Here is a more controllable experiment illustrating the same phenomenon. There is no stopcock at the bottom, and this vessel is open to the atmosphere on top, and yet this clay suspension does not flow. I can put this simple piston here, place this small weight on it, still no flow. Now a larger weight. It flows, but very slowly. A much larger weight. The flow is fairly rapid. I take the weight off. The flow stops. In a state of equilibrium, this material can support a shearing stress up to a critical value called a yield value. Even with materials not having yield values, the Newtonian fluid cannot explain many flow phenomena. For many of these, a more general model, that of the memory fluid, does provide an explanation. For the memory fluid, the pressure is isotropic in the equilibrium state where no changes of either the stress or the deformation are taking place. In relative motion, however, in contrast to the Newtonian fluid, the history of the deformation is significant. Instead of a linear function, the memory fluid reveals nonlinearities. In fact, nonlinearity affects both the shear stresses and the normal stresses. So, for the memory fluid, the stress is a nonlinear function of the history of the deformation gradient. For this model too, flow problems are solved by expressing this assumption mathematically and using the momentum equations. First, we will look at experiments demonstrating that stress does depend on the history of the deformation. This material exhibits both viscous and elastic characteristics. Honey has a high viscosity but no elasticity. Remember the fluid ball? It was like an elastic solid during the short impact of bouncing. An elastic solid has a preferred configuration to which it will return when stresses are removed. A viscoelastic fluid behaves similarly if the stress has been applied only for a short time. But in contrast to the elastic solid, the fluid's memory is not perfect. This time-lapse sequence shows that if the stress acts for a time long compared with the relaxation times of the fluid forgets its previous state. In reality, it took 45 minutes for the force of gravity to change the ball into a puddle. This is a container of high polymer solution. I'll drop in a steel ball. Again. Once more in slow motion. This liquid too is viscoelastic. Here's some more polymer solution. I can put this cylinder into it and turn it a full 360 degrees. When I let go quickly, it returns almost half the distance. This time I'll hold it for a few seconds. Since the fluid has a fading memory, when I do let go, the recovery is a much smaller fraction of the original deformation. We can make quantitative measurements of viscoelastic behavior in this type of apparatus. The test liquid is confined in this annulus. The outer cylinder is held stationary, and we can apply a torque to the inner one with this weight, which we can hang there. A trigger here releases the mechanism. To remove the torque, there is a slip toggle there. We can record the response of the inner cylinder, that is, its angular rotation as a function of time, with the pen on a chart moving at constant speed. The weight of the recording pen is counterbalanced by this small weight. We have, of course, designed this experiment to minimize extraneous effects arising from the inertia of the fluid, the inertia of the moving parts, and from friction. The first experiment is with a Newtonian fluid designated by the letter N. A constant velocity is attained almost at once since inertial effects are small. Now the applied torque is zero again, and the cylinder stops immediately. This time, the fluid in the annulus is viscoelastic. A constant velocity is not immediately obtained. Even though the stress is constant, the deformation and the rate of deformation are changing with time. Now the weight is disengaged. Let's watch that again. takes a while for the viscoelastic fluid to acquire the steady state motion appropriate to the constant torque. When we remove the torque, we see the cylinder actually reverse its direction. Although no torque is being applied, the material is deforming because of the elastic character of the fluid. Not all the energy used to produce the flow was dissipated. Some was stored and then recovered. We have looked at some experiments showing that the stress depends on the history of the deformation. To illustrate nonlinear behavior, we shall do experiments in which the time-dependent characteristics of the fluids are negligible. Here we have two identical reservoirs with two identical outlet tubes. One contains a Newtonian fluid, the other a non-Newtonian. The levels are the same. At first, the non-Newtonian fluid flows faster.